Well, we're going to do some practice now with tangent planes. We're kind of going to do a little bit different in that this time we're focusing on one very special topic, and we'll do problems ranging from very, very simple to a little bit more fun, almost like puzzles when it comes to finding tangent planes. Now, as always, the way we get better at doing these problems is through doing them. It sounds strange, but that's what you need to do. You do the work. So if you're following along with the video, make use of the pause button. If you see a problem that you like, definitely pause me and try it out yourself first so that you can have the joy of solving the problem. And I hope you do say, wow, these can be fun. And there's a lot of pleasure that comes from solving a really good, challenging problem. Well, let's start having some joy, and let's begin. So, our very first problem. Find the tangent plane to the surface, z, which is a function of x and y, which is x squared y minus 3x squared plus y cubed at the point minus 1, 1. Now, this is really just a nice, gentle warm-up. So we're not going to do very many of these. In fact, this might be the only one where we explicitly do it, where it says find the tangent plane. A lot of the rest of them are going to be like, well, I got to look for things. So let's think about the formula. So when we talk about the tangent plane at a point, what does it become? Well, we're talking about specifically the following. It's the value of the function at the point AB plus the derivative with respect to x at AB times x minus a plus the derivative with respect to y at AB times y minus b. That's it. That's the formula. Okay, so it's not so bad. And in essence, we have to figure out, okay, a, b, f of ab, f sub x at ab, and f sub y at ab. But things are given to us. So for instance, we know what a and b are because that's stated. So in terms of a and b, that's this point right here, a comma b. Perfect, perfect. So really, what do we need to do? We need to take our function, take some partial derivatives, the f sub x, f sub y, evaluate, and then we're good to go. So let's do our partial derivatives. So we'll write down our function again for reference. So we have our function, f of xy, which is x squared y minus 3x squared plus y cubed. So f sub x, which remember, that means we're taking the derivative with respect to x. X is our variable. We treat all the y's for the time being like constants. So we go through term by term. Derivative of x squared y, well, that would be 2xy. Derivative of 3x squared, that would be 6x. Derivative of y cubed would be 0, because we're taking the derivative with respect to x, so y cubed acts like a constant. In a similar way, we do f sub y. F sub y of xy, well, go to the first term, x squared, because x squared is a constant times y. Derivative of 3x squared, 0. There's no y. Derivative of y cubed will be 3y squared. Good. Now, remember, we don't take these and plug them in. So in other words, it's not like f sub x is going to be this 2xy minus 6x that goes there, because we need to do an evaluation. It's a very important thing. Sometimes people forget to do an evaluation, and they end up with something which is definitely not a plane. So if you're looking for a tangent plane, your answer better be a plane at the end of the process. If it's not, whoops, okay, something is very wrong. Well, what do? We plug in our point. So we need to plug in f of minus 1, 1. Okay, so just go through term by term. Minus 1 squared is 1 times 1. 1. 3 times negative 1 squared. Okay, well, be careful. Negative 1 squared is positive 1 times minus 3. That's minus 3. 1 cubed plus 1. Okay, so that's negative 1. F sub x, at negative 1, 1. Okay, so it's 2 times minus 1 times positive 1, which would be minus 2. Minus 6 times minus 1. Well, that'll be plus 6, which gets us 4. F sub y at minus 1, 1. All right, minus 1 squared is 1. 3 times 1 squared is 3. And we end up with 4. Well, so in this particular case, it turned out f sub x and f sub y at the point were equal. Generally speaking, that doesn't happen. That's just a coincidence. So don't read too much into coincidences. But now we're really almost done. The last thing for us to do is to put in our values, right? So we have that f at AB is negative 1. F sub x at AB is 4. Of course, A is minus 1. F sub y at AB also 4. And then B is plus 1. And so, putting it all together, we get the following. Our tangent plane would be z equals minus 1 plus 4 times x minus minus 1. We can write that as x plus 1 plus 4 times y minus 1. That's perfectly fine to leave your answer like that. You could also clean it up. You can say, look, that's really 4 times x, 4 times y, and then what do we have? We have minus 1, a plus 4, a minus 4. Well, the 4's and minus 4's cancel, so we end up with a minus 1. And there we go. That's it. There's our plane. Not so bad. So really, when you're asked to find a tangent plane, and you have a function, you say, okay, this isn't so bad. I just do what is f sub x, what is f sub y, what's the value of the function, put everything together, and life is good. All right, well, good warm-up. Now let's do some more. Try looking at some other problems here. Our next one. Find all points x, y at which the tangent plane to the surface z equals x squared minus 3xy plus 5 halves y squared minus 2x plus 3y is parallel to the plane given by the equation 2x minus 4y plus z equals 6. Okay, all right. So what are we after? Well, we're after some points. And so that means our final answer should be some points. We'll keep that in mind as we get towards the end and say, is this our answer? Well, if it's a point, well, maybe. So, but what do we need? Well, we have to be parallel to this plane. All right. So our idea is we have this surface out in 3 dimensions, and we have tangent planes. And somewhere else is this other plane floating out in space. And we want to say, look, I don't care about most of the tangent planes. I only want the tangent planes which are parallel. So one of the things we have to decide is, how do we figure out when planes are parallel? So we have to sort of think back into our geometrical intuition, which is why we spent time trying to develop our geometrical, it's a fun word to try to say, intuition. So planes are parallel if their normal vectors are parallel. You always want to be careful, and you don't want to be getting into the trap when you say the normal vectors are the same. Well, because that's not quite true, right? You can always scale. Now the good news is we have our normal vector. You read off the coefficients. So the normal vector here would be 2, minus 4, 1. All right, so that says we need the tangent plane vector to be parallel to this vector here. Now, before we get too far down, let's just think about what's true in general. So let's start with the equation for a plane. So, or the tangent plane. Let's be more careful here. If we write down the formula for our tangent plane, it's f of ab plus f sub x at ab times x minus a plus f sub y at ab times y minus b. Now, if you expand this, you'll say, okay, well, you're going to end up with f sub x at ab times x. You're going to end up with f sub y at ab times y, and then you're going to have a number. And this is just shorthand for a number. Kids these days might call it a hashtag, but us old people would say number. And okay, so it's some value, right? The value coming from f of ab, f sub x at ab times minus a, f sub y at ab times minus b. So if we gently nudge things around, and there's all sorts of ways we could do it. So for instance, if we move these terms across, we can say, well, look, minus fx at ab times x minus fy at ab times y plus z has to equal that number, whatever that number is. I'm just using that as a shorthand. So we're like, because now we're like, look, we can read off our normal vector. The normal vector here would be minus f sub x at ab, comma, minus f sub y at ab, comma, 1. All right, cool. Now we say, okay, what needs to be true? Well, we look at these two vectors and we say, well, these vectors have to be multiples of one another. And we're kind of in luck, because look at what happened in the third entry. They're actually already match, which means that since they have to be multiples of each other, in fact, not only are they multiples of each other, they have to be the exact same. Good. So what needs to be true? Well, since the third entry matches, that means that the other entries also need to match. So we come to the conclusion that we need minus fx at ab equal to 2, or another way to say that is f sub x at ab has to be negative 2, and f sub y at ab would have to equal 4. So we're after points ab where these are true. So let's take a look at our partial derivatives. Now, we haven't explicitly said what f is, but f is this whole expression here. So this part right here, this is our f of xy. So let's see, if we take f sub x, we'll just do that first. We would get 2x minus 3y. The 5 halves y squared would be 0 because we're taking f sub x, which means derivative with respect to x, and minus 2. And when we do f sub y at xy, what do we get? Well, we'll end up with minus 3x plus 5y and plus 3, because we're taking derivative with respect to y. And now we say, great, we're almost done. So, in fact, this is looking very promising. Because what can we do? Well, at this point we can say the following. We say, well, this translates into, when we plug in AB here, we need 2A minus 3B minus 2. So that's plugging AB into f sub x equals minus 2. And when we plug it into f sub y, minus 3A plus 5b plus 3 has to equal 4. Okay? Yep, f sub y at ab equals 4. Or, cleaning that up, we need 2a minus 3b to equal 0. And minus 3a plus 5b has to equal 1. All right. Well, now we just have to start thinking, how do we figure this out? What's our solution? Well, there's a lot of ways we could proceed. So one thing we could say, well, let's do it this way. This is so tempting, right? We could say 2a equals 3b. So let's multiply through by 2. So we have minus 6a plus 10b equals 2. But look, minus 6a, what can we do? Well, minus 6a is the same as minus 9b, because I can replace 2a by 3b. So minus 9b plus 10b equals 2. So that gets us to the conclusion that b equals 2. Perfect. Well, if b equals 2, what should a be? Well, plug in b equals 2 up here, and we're going to get that 2a better be 6, or a equals 3. And therefore, our final answer, look, we only have a single pair that satisfies the equation, which means there's one point that makes it work. And so our answer is the point 3, 2, a, b. So that's the only place where, when we look at that tangent plane, we're going to be parallel to the given plane. And remember, we were looking for points. Now, they could have said, find the plane. Well, then we would have done something else. But for now, we just needed the point. And we got it. We got our point. Good. Success. Success. We love it when a plan comes together. So, let's do another one. So here we go. A plane is tangent to the surface z equals a third x squared plus a half y squared, and perpendicularly intersects with the line 4 plus 2t, 3 minus 2t, minus 1 minus t. And the question is, where does the line and plane intersect? So we're going to be looking for a point in three-dimensional space. All right, well, this should be a little fun. So we have to think about what's true. Well, certainly we know how to find intersection of line and plane, because we did that when we talked about geometry. Namely, a plane has some relationship between x, y, and z, and we plug in the appropriate pieces for the x, y, and z that come from the line and solve for t. So if we had the plane, we'd be in great shape. We don't have the plane. not yet. Well, we'll get there, right? We always have to start somewhere. So we start thinking, okay, what needs to be true? Well, let's work by finding the plane. So we look at our equation. It's fairly not complicated. It's fairly straightforward. And we say, okay, what needs to be true? Well, we know that this line is perpendicular to the plane that we're after. That's important to us. What does that mean? Well, we have this surface, and we kind of know what this surface is. It's a bowl. It's we can, if we wanted to sound very fancy, we can say it's an elliptic paraboloid. But if we want to just, among friends, we're like, it's a bowl. Yes, it is a bowl. That's correct. And then what we have is somewhere we have this line running through space, and it's doing something. And what are we after? Well, we want to find a plane. I don't know, let's say it's at this point right here. So it's this plane such that when we look at where the line hits the plane, and it's a tangent plane too, let's be clear, that this is perpendicular. That's what we're after. Okay, so there's a lot of moving parts here, but let's start unraveling it. We know that the line is perpendicular. And whenever you see something about perpendicular, you always start thinking, okay, I need to start spouting out things which are perpendicular. The normal vector is perpendicular to the plane. And therefore, we can say, aha, this plane should have a normal which is not necessarily equal to, but parallel to the direction of the line. Because the direction of the line is going to be perpendicular to the plane. Okay, so we should sit down and say, well, what is the direction of the line? And we can read it off. That's why it's useful to be able to recognize our geometrical tools. That helps us, we can read off normal vectors from the equations of planes. We can read off direction vectors from the equations of lines. And remember, this is the vector format for a line. So you can read it off by thinking that this is our x, y, and z. So our normal is going to be some multiple of 2 minus 2 minus 1. Okay, so there's our basic setup. Now, let's get into our actual surface. So we know the normal vector that we're shooting for our tangent plane. Say, okay, since we now know that, the next step for us is to figure out the right tangent plane. So for that, we can focus in on our plane here. So we have f of x, y, which is 1/3 x squared plus 1/2 y squared. All right, it's not so bad. Now we'll look at our f sub x, and here, pretty simple, 2/3 x, and our f sub y. And again, that's really simple. Y. Can't, it's about as easy as you could possibly hope for. And using these, we can now write down our formulas for our tangent plane. So it's our function at AB, then plus fx at AB times x minus a, and fy at AB times y minus b. So let's put everything in. So we're going to get 1/3 a squared plus 1/2 b squared. That's the f at AB. Fx, well, that'll be 2/3 a, right? Plug in for a. So 2/3 a times x minus a. Fy, well, that'll be b times y minus b. All right, good. And now we will gently coax this through and clean it up. So what do we have? We have z equals 2/3 a x. So I'm just going to multiply through. And b y, that goes there. And then we're going to get 1/3 a squared, subtract 2/3 a squared, which becomes minus 1/3 a squared. We're going to have 1/2 b squared, subtract b squared, which is minus 1/2 b squared. So now if you give us any a and b, we can be like, there's our tangent plane. No problems. Here it is. Pow! Cool. Of course, now we got to figure out, what's the right a and b? Well, we're almost there. We're almost there. So if we were to move, let's say, the z across for just a second here. So 0 equals 2/3 ax plus by minus z minus 1/3 a squared minus 1/2 b squared. I just want to be able to make sure I read off my normal correctly. From here, we say, okay, the normal is what? Well, it's these coefficients here. So it would be 2/3 times a, and then b and -1. So what needs to be true? Well, we compare this normal with this vector. That's also a normal to the plane. It means they have to be multiples of each other, and of course our last slots already lined up. So we come to our great conclusion. We're almost done, right? Well, maybe. Well, what do we know? We know 2/3 a has to equal 2. Okay, well that's not so hard to solve. Multiply both sides by 3/2. A better be 3. And we know that b has to be -2. Also not so hard to solve because that says b better equal -2. Like I said, not hard to solve that one at all. All right, now, are we done? No, we're not. We still have like 2 or 3 more steps, right? Because what do we need? We need to find a point where the line and plane intersect. So we have to find the plane. We can't find the point of intersection if we don't have the plane. So our next step is find the plane. All right, but that's not hard. Because why? Well, because we actually have it. It's right here. Or it's right, either one, doesn't really matter. And what we do is we plug in our choices for A and B. So we're going to get Z 2/3 times 3 times X. So that'll be 2X. B times Y, minus 2Y. Then minus 1/3 times A squared. Well, A is 3, so 1/3 times 9 makes minus 3. 1/2 B squared. Well, B is -2. Square that before. Minus 1/2 would be minus 2. So we plugged in A and B because now we know our A and B, so we can plug it in. Okay, we have our plane. Next, and we're getting close, is we say, okay, we need to now find the intersection point. And for that, we say, okay, we know X, Y, and Z. So we're going to put these in, X, Y, and Z for X, Y, and Z. So what do we have? Well, we're going to get -1 minus t, that's our Z, equals 2 times 4 plus 2t, that's our X, minus 2 times 3 minus 2t, that's our Y, and then there's minus 5 on the end. Okay, well, let's multiply this out. Let's see what we have. -1 minus t equals 8 plus 4 times t minus 6 plus 4 times t and minus 5. All right, well, this doesn't seem so bad. What can we do? We can move stuff around. So, for instance, we can add the t across, because then we have a 4t and a 4t, and another t, which should make it 9t. On the other hand, we can move these values across. So we have -8, and we'd add 6, and we'd add 5. Okay, there's a lot going on here. Let's make sure we get it right. Well, maybe let's just combine these. So I have 8 minus 6 would be 2, minus 5 would be -3. When I bring it across, I add 3, and there's a -1 here. That would make it 2. So we get 2 equals 9t. All right, well, so what does that say about our choice for t? It says t has to equal 2/9. All right, good. We now have our t. We figured it out. Okay, but now what? Well, that's the right choice for t, where the plane and the line intersect. And we come back and we plug it in. So we get the point. We're going to get 4 plus 2 times 2/9, which is 4/9. 3 minus 2 times 2/9, which would be 4/9. And then -1 minus 2/9. And that's our answer, but we can clean it up a little bit. For instance, 4 is 36 over 9, plus 4 over 9 makes 40 over 9. 3 would be 27 over 9. Subtract 4 over 9. Well, that's 23 over 9. And then -1 is the same as -9. And, of course, subtract 2 more makes -11 over 9. And there we go. And That's the answer. 40 over 9, 23 over 9, minus 11 over 9. Wow, what an answer. Definitely, I don't think we would guess that they just had to do something with ninths at the final answer. But that's all right. We didn't have to guess. We were just careful and methodical. We worked the problem and from start to finish. And, there you go. There you go. Life is good. What a fun problem. All right. Well, let's try another one. Here's we go. So, we're given that the line 3, 2, 5 plus t 3, 2, negative 1 and the line 3, 2, 5 plus t 6, negative 2, negative 5 are both tangent to the surface z equals f of xy at the point 3, 2, 5. Well, that's pretty good. They both go through the point 3, 2, 5. All right. We're also told f is differentiable at that point, which means we can take partial derivatives. But really what that means is that locally it looks flat. So in other words, you have the surface, and it might be bumpy, but zoom in, zoom in, zoom in. As you get closer and closer and closer, it looks more and more like a plane. So, our problem. Find f sub x at 3, 2 and f sub y at 3, 2. And there's a hint. How do you write the tangent plane in terms of the partials? Well, let's think about what's going on here. So normally, if we have a surface, so let's suppose we're in space. Let's draw ourselves some axes to just help sort of cement what's going on. And suppose we have some sort of function, and maybe it's doing something a little bit like that. Okay, so we have this function going on, and we're trying to understand the tangent plane at a particular point. So we're after the tangent plane that's sitting at that particular point. Well, the way we've developed the ideas is to say, we look at the partial derivatives. And when you're looking at partial derivatives, what you're doing is you're really looking at slices of your function. And you look at a slice where, for instance, maybe you hold y fixed and you let x vary. So that's this slice here. And then that will give you your f sub x, which essentially gives you a piece of your tangent line. It gives you a line inside of your tangent plane. But of course, you could have done a different slice. And if you choose a different slice, you can hold now x fixed. And what you'll end up with is you'll end up with something where only the y varies. And you find the f sub y. And really what you recover is another line in your tangent plane. And you say, well, once you have these two partial derivatives, you have your tangent plane. So what's different about this problem? Well, the difference here is that we were not going to be given fx and fy directly. We're going to be told something else. So in essence, what's happening is we still have our same surface. That hasn't changed. We're still after our same plane. That hasn't changed. But what's changed is our information that we have. So that instead of knowing what our lines where we hold x fixed or we hold y fixed are, because that's the information that we're given when we talk about that tangent plane, what we have is we say, look, there are two other lines out there and going through this point. So we have two other lines that are going to be tangent to the surface. So the key idea is that two lines tangent to the surface give us what? Well, they give us enough information to get the tangent plane. That's sort of the fun idea. If we understand that concept, then this problem will be enjoyable. And if we don't, we're going to be spending a lot of time doing this problem. Now, you say, okay, cool. So I have these two lines, which are tangent to the surface. And it makes sense. If I have a tangent line, it's inside my tangent plane. And I have two of them. So we say, okay, so I can form my tangent plane from my tangent lines. So how do we go about doing that? Well, the way we do it is we just say, okay, let's step back and forget about the fact that we're tangents and just say, how do I form a plane if I know I have two lines? The answer is, all right, grab the direction vectors, and we see what they are. They're 3, 2, minus 1 for the first line, and they're 6, minus 2, minus 5 for the second line. So we're going to take these two, and we say both of these vectors are vectors which are in our tangent plane, because they're both direction vectors of tangent lines. And so by crossing them, we will get a normal. And we're going to emphasize the word a, as we often do, because normals are not unique. So, wow, a walk down memory lane. The good old days when we got to do lots of cross products. Well, hopefully it's not too bad. Okay, let's see. We have I times 2 times minus 5. That's minus 10I. J times minus 1 times 6. Minus 6J. K times 3 times minus 2. Minus 6K. 6 times 2 times K is 12K. But we're going uphill, so we have to subtract. Minus 2 minus 1 times I is 2I, but we have to subtract. Minus 5 times 3 is minus 15. We've got to subtract, so it becomes really a plus 15. And what do we end up with? We end up with minus 12, comma, 9, comma, minus 18. Okay, well, let's just factor out what they have in common, just to make it a little bit easier to work with, because we can factor out common terms. So 3, negative 4, 3, negative 6. Now, before we proceed any further, let's step back and make sure we got our answer right, or at least get some confidence that we got our answer right, which we do by doing dot product. Okay, so let's see, minus 12 plus 6 plus 6, 0. Good. Minus 24 minus 6 plus 30, right? So that's minus 24 minus 6 is minus 30 plus 30 is 0. Good. Done. Done. Okay. Success. Success. Now, what does that tell us? Well, it tells us that our tangent plane has the form minus 4x plus 3y minus 6z equals something. Well, we're almost done, but in fact, we know what the something is, because it told us on 3 times, 325, 325, 325. Point is on our plane. So if we plug that in, what will we have? Well, we'll have minus 12 plus 6 and minus 30. Okay, well, what does that turn out to be? It's 6, and then we're subtracting 42. Okay, well, that's what? Negative 36? All right, it's a big number. But the important thing is, for right now, this is our tangent plane. Okay, good. Good. Now, how do we use that? Well, the tangent plane, keep in mind, in some sense, the tangent plane actually contains all tangent lines. All of them simultaneously. It's kind of a cool idea. And once we know 2 of them, that's enough for us to figure out the whole thing. So even though there's infinitely many tangent lines, 2 suffice to find the whole tangent plane. But, of course, we have to stop and say, but where do we go from here? Because it's important to make sure that we know where we're going. Now, the answer is to say, look, what are we after? We're after f sub x at 3, 2 and f sub y at 3, 2. So how do we find that? Well, we're going to stop for a second and go back and sort of read the hint. How do you write the tangent plane in terms of partials? Well, if you remember, we've done this a couple times. It becomes z equals fx ab times x plus fy at ab times y plus a number. I'm just worried about the partials. And so we say, okay, this is our tangent plane. If we can make it look like this, we read off our answers and life is good. So we're going to do a little bit of rearranging. So let's swap these terms. So we can, for instance, say 6z is equal to minus 4x plus 3y plus 36. Or we could say z is equal to, divide everything by 6, negative 4 over 6 is minus 2/3. 3 over 6, 1/2. 36 over 6 is 6. Which means now we play our great matching game. And we say, aha, our number is 6. Well, that's not something we really care about. But here's things we do care about, f sub y. Because we have it z equals, so it's the coefficient of a half. F sub x, that's going to be negative 2/3. So our final answer is we get f sub x at 3, 2, because a and b is 3, 2, is equal to minus 2/3, and f sub y at 3, 2 is equal to positive 1/2. And there we go. Aha! Beautiful, beautiful problem. And kind of this one is fun because it's really emphasizing the geometry of what's going on. Hey, you have this notion, even though you have a surface, you can talk about a tangent line, which just touches it. It's just a line which is in your tangent plane, also passing through your point. And now we say, oh, well, you'll give me 2 of them. I'll give you a tangent plane. Cool. And then we're all happy because we're making progress and solving problems. And life is good. And good times, good times. Well, let's keep moving forward. Okay, our next problem. Consider the surface z equals x squared plus y squared. You'll notice we do a lot of examples that involve very simple surfaces. Not because they're the only surfaces that are important, but just because we're focusing more on the ideas than on trying to sort of add complicated computations. Beautiful ideas will always translate into complicated situations, but we don't want to start obfuscating by making things complicated. So don't think like, oh, well, you have to have bowls if you're going to talk about tangent planes. No. You don't have to. We can do tangent planes for all sorts of wonderful things. All right, so there's 2 parts. Part A, find the tangent planes to the surface at 1, 2, and 2, negative 1. Okay, well, let's do part A, and then we'll talk about part B. So what do we have? So when we think of our x squared plus y squared, this is our f of xy. So we'll write that down again. F of xy is x squared plus y squared. So f sub x, xy, is 2x. F sub y of xy is 2y. Okay, that's no surprises there. Now what? Well, now we have to talk about at particular points, right? So we have to talk about what happens at the point 1, 2. So we're at 1, 2. And then we're going to talk about what happens at 2, negative 1. So when we are at 1, 2, 1 squared plus 2 squared, that's 1 plus 4, which gives us 5. 2 times 1 is 2. 2 times 2 is 4. At 2, negative 1, 2 squared plus negative 1 squared. 4 plus 1 is 5. And then we're going to have 2 times 2, which is 4. And 2 times minus 1 is minus 2. All right, so those are our values. And now we can write down our planes. So we have z, let's do 1, 2 first, is the value of the function, 5, plus the derivative with respect to x at the point, 2, times x minus the x value, x minus 1, plus derivative with respect to y at that point, 4, times y minus the y value, y minus 2. And we can, if we wanted to, just expand this. This is 2x plus 4y, 2x, 4y, and then we have 5 minus 2 minus 8. So that makes it minus 5. Then we have our other plane. Okay, z equals 5 again, plus derivative with respect to x, 4, times x minus our x value, so x minus 2, plus the derivative with respect to y at the point, which is negative 2, so minus 2, y minus our y value, so y minus a minus 1, makes a y plus 1, which gives us what? Well, 4x minus 2y, and then we have 5 minus 8 minus 2, and actually minus 5 again. Okay, good. Now, you might be noticing if you've been doing all the problems all the way through, hey, I see beautiful things where the value of the function ends up being subtracted at the end. Well, that's kind of because we're doing very simple bowl-like shapes. Don't read too much into that. Coincidence because we chose beautiful problems to work with. Okay, so that's it for part A. So here we have our lovely answers for part A. Good. And lots of space left. Well, we still have a lot of problem left, right? Part B. Find a point, AB, it says there's only one, so that the tangent plane at AB is perpendicular to both the planes that we found in part A. Aha! Okay, so we have one plane, actually we have 2 planes, right? And we said, look, there's a third plane out there which has a property, it's perpendicular to both of them, and it's also tangent to our surface. And so we have to find it. And, well, actually, we're not finding the plane. We're really finding the point where we have our tangent plane. Okay, well, this will be interesting. They put a little side note there for us, a parenthetical comment. I suspect it might be useful. Let's see what it says. Recall, 2 planes are perpendicular if their normal vectors are perpendicular. Like, okay, so that gives us an idea. So what we can do is we can come to these planes we found in part A, and we can be careful to read off their normal vectors. Let's read off the normal vectors. Okay, so we do it by looking at the coefficients, but be careful here. Let's do it for the first one. It would be 2, 4, right? 2 in front of the x, 4 in front of the y, and negative 1. Why negative 1 and not positive 1? Well, because the z, it's on the wrong side. You really have to subtract the z to put it on the right side, and then it would be the right one. Okay, similar, we're going to get 4 minus 2 minus 1. So those are the 2 vectors, which are the normals to the planes that we already found. So, okay. So we want to be perpendicular to both planes, which means the normal vector for the plane that we're looking for has to be perpendicular to both simultaneously. What technique should we use? Does anything cross your mind? Yeah, it's a cross product. Okay, that's not very surprising. Oftentimes when we see a problem which uses words like perpendicular, cross products are going to play a role at some point. Okay, so, well, more practice doing cross products. Good stuff. I know we learned that stuff for a reason, right? So let's see, ijk, 2, 4, negative 1, 4, negative 2, negative 1. Okay, so we're going to get minus 4i, minus 4j. minus 4k. Oh, there's a lot of minus 4s going on there. Plus 16k. Wow, my goodness. But wait, it's got to subtract it because of the direction we're going. All right, well, that's fine. Then it would be 2i, but we need to subtract it. So minus 6i. And minus 2j, but we have to subtract it. So really add 2j. So it looks like, what do we have? Minus 10, comma, minus 2, comma, minus 20. Well, what should you do? The answer is we check our work, right? Because we don't want to lose points. So we do dot products really quickly. Minus 20. Okay. And then we have minus 8 and plus 20. Well, that doesn't go to 0. Okay, good. That's fine. That just means we made a mistake. So we'll check our work. Let's see where we went wrong. Okay, so let's see. Minus 10, minus 2, minus 20. So it means we made a mistake here. Okay, minus 4i, that's good. Minus 4j, minus 4k, minus 16k. Then it'd be subtract. Oh, there we are. See, minus 2 times minus 1 times I. It's not 6. Whoever said 6. Who said that? Who told me 6? Oh, wait, it was me. I did that. Well, okay. So it's really 2i, but we subtract it. So this is going to be a minus 2i. So that makes this a minus 6. Okay, now let's check and see, okay, does that work? So minus 12 minus 8 is minus 20 plus 20. That's more promising. Here, minus 24 plus 4, that's up to minus 20 plus 20. Good, good. Okay, so there we have our normal vector that we want. Okay, of course I used the wrong. I shouldn't use the normal vector. We want this to be parallel to the normal vector for our plane. So let's now jump over to talking about our plane. That's a tangent plane. If we think about our surface here, well, what is it? We can say, look, we have our expressions here. So our generic vector will be z equals our f, a, b. I said generic vector. I should say generic tangent plane. F sub x at ab, x minus a, f sub y at ab, times y minus b. And so you can actually read off the coefficients. And you can say, hey, our generic tangent plane has the coefficient of x, f sub x at ab, coefficient for y, f y at ab, and the coefficient for z, if we brought it over, would be negative 1. Now, that's very generic. F sub x at ab would be 2a, f sub y at ab would be 2b, and negative 1 is negative 1. So we say, okay, now we want these two vectors to be parallel. When are two vectors parallel? Two vectors are parallel if we can scale one to get the other. And we look at the third entry because that's really going to be the one that's the telltale entry. Is there a way to get from there to there? It doesn't really matter which way we go. So for instance, I can multiply here by 20. I could say, look, 40a, 40b, negative 20. That's what our vector would look like for the normal vector for the tangent plane at AB. And now we say, okay, well, what does that tell us? Well, if we now set things equal, we come to the conclusion that, look, this coefficient has to match with that one because the thirds match, so the others have to match as well. So we have that 40 times a has to equal negative 6. And 40 times b has to equal negative 2. So if we now divide, okay, So negative 6 divided by 40, well, we can certainly divide out by a factor of 2 first. So we get that a should equal negative 3 over 20, and b should equal to minus 1 over 20. And there we go. That's it. We're done. We're done. Okay, well, that worked out pretty well. Things were relatively clean. We like it when a problem comes together, right? Of course we do. Well, good. Let's keep going. More problems to do. Well, this one is a good one. It's actually one of my favorites. So, here we go. There are two planes which are tangent to the surface, z equals x squared plus y squared, and pass through both of the points 1, 0, 0, and 0, 2, 0. And one of the planes is just the plane z equals 0, and it says find the other one. All right, well, what's going on here? If you actually plot this surface, it's very easy to plot because this is our bowl, classic bowl-shaped surface. And so what we have is we have some elliptic paraboloid, and it's coming down, and it sits right on the origin. And what we're looking for is we're saying, okay, there's a point, 1, 0, 0, which is a point here along the x-axis, and a point 0, 2, 0, which is a point along the y-axis. And we're saying, okay, there's some tangent planes that are tangent to the surface and also contain these 2 points. Now, one of them is really easy to spot, and that is if you just think about the xy plane. See, the xy plane, that's definitely going to be tangent to the surface because the bowl sits on top of the origin. So at the origin, it looks flat, and it contains the points on the axis. Now, here is sort of the fun thing when you think about the geometry. If I'm going to contain these 2 points, I can think of these 2 points as there's a line through here, which I'm allowed to pivot. So when I'm flat, I'm going to be tangent, and then as I pivot, I come off, but then eventually I'm going to hit the surface again. So there's a tangent plane when I'm flat, and then there's going to be another plane where I'm slightly pivoted through that line, which I'm going to hit that surface. Okay, so that's our goal. Now, when we see problems like this, and by this time we're like, yeah, we've seen things not so far off from this, it's not always so clear where to start. Because you're like, well, I'm trying to find one specific plane. How do I do it? And so there's this idea. So here we go. And this is a really very valuable idea. We'll just give it to you for free. We're just going to tell it to you. Wow. Shh. Don't tell your friends. No, do tell your friends. We want people to know. And it's really simple. If we need to find a tangent plane, in other words, a tangent plane, so I'm emphasizing the word a, tangent plane. This is not a as some sort of special symbol. Then find all the tangent planes and pick out the one you need. So in other words, instead of humming and hawing about, I need to find one particular tangent plane because I don't know where to start, they'll say, well, look, let's not worry about finding the specific one. Let's just find all of them, and then we'll pick the one we need. All right, good. So that's our basic idea. It's actually an amazingly useful thing to do, is to go through and say, okay, I'm going to find everything that could be a candidate, and then I'm going to do some weeding out process. So the way we find all the tangent planes is we go through and run our formula. So our formula for a generic tangent plane, it's the value of the function at AB plus f sub x at AB times x minus a plus f sub y at AB times y minus b. Now, for us, what's our function? Well, our function it's x squared plus y squared. So we're going to have, look, if this is our function, so our function of x, y is x squared plus y squared. Then our f sub x is 2x, and our f sub y is 2y. So we get that our tangent plane, when we plug in AB, is a squared plus b squared, so that's the value of the function, plus f sub x at AB, okay, that's 2a times x minus a, and f sub y at AB would be 2b. Or is it not 2b? No, it is 2b. All right, 2b times y minus b. And if you clean that up, we get 2a times x plus 2b times y, and then we're going to have minus 2a squared minus 2b squared, and there's a squared plus b squared, so minus a squared plus b squared. Okay, so here we go. This is our grand collection. So we can say, okay, you give me an a and b, there's my tangent plane. I've essentially described every single tangent plane to the surface, all simultaneously, all having a good time. Wonderful, wonderful. This is great. Now where do we go? Well, the next place for us to go is say, okay, we're going to pick out the one we need. So we say, okay, we know for sure, as long as it's one of these, that we're automatically tangent, because these are all tangent. So we go back and say, well, what else do we need? That'll help narrow it down. And in particular, notice how we have two things. We have A and B. So whenever you have two parameters you can play with, two knobs, if you will, that you can adjust, then you should say there should be two pieces of information. And there are two pieces of information. Namely, that 1, 0, 0 and 0, 2, 0 are points on the plane. So we can now plug 1, 0, 0 in for x, y, and z, and 0, 2, 0 in for x, y, and z. That'll give us two equations to work with. Okay, so let's see what happens. So when we plug in 1, 0, 0, well, we're going to get 0 in for z, so 0 is equal to 2 times a times 1, so that's 2a, 2 times b times 0, all right, minus a squared plus b squared. All right, if we plug in the other point, 0, 2, 0, what do we see? Well, again, z is 0. Now we get 2 times a times 0, plus 2 times b times 2, so that's 4b, and then the minus a squared plus b squared. Well, if we combine these equations together, we come to the conclusion, it's a really nice conclusion. We say, look, 2a has to equal a squared plus b squared has to equal 4b. All right, well, that's great. So what can we do to help us solve? Well, if I know that 2a equals 4b, I say, aha, cool, that tells me that a, whatever it is, has to be twice whatever b is. So now I know that a equals 2b. Is that really enough? Well, yeah. Let's take the fact that we know a equals 2b, and I'm going to plug that into the first equation. So, if we do that, what do we get? Well, here we go. We'll put it up here because we're running out of space down below. We'll get 0 equals 2a, because I'm replacing a by 2b, minus, and then there's a squared. Whoops, I need to replace a by 2b, so I did that wrong. So 0 equals 4 times b, because a is 2 times b. So 4b, a squared, 4b squared plus b squared, makes plus 5b squared. All right. Well, that says, hey, 0 has to equal b times 4 plus 5b. All right. So what does that say? Well, it says there's two possibilities. B equals 0 or B equals negative 4/5. All right. So those are our two possibilities. B equals 0 or B equals negative 4/5. Okay. Well, what do we do from here? Well, we got to think about them. Suppose B were 0. If B were 0, A would be 0. And if B and A are 0, we get 0 and 0 and 0, which means we get 0, which says we get the z equals 0 as the solution. Okay, we already knew about that. We're asked to find the other one. But it's a good sign that we found this one. You see, because we knew it was a solution, so it should show up in our computation somewhere. So the fact that we found it, thumbs up for us. We're doing great. Okay, so now we know, hey, B is negative 4/5. How about A? Well, that's not hard. That says A has to be twice that, so that's negative 8/5. So now we know our A and our B. Good. Except, aha, I made a small mistake. Let me go back and correct it before we go too much further. Can you see my mistake? You probably already spotted it a while ago. I forgot about the minus sign. So this should be a minus here. That should be a minus there, making this a plus, making that a plus. So 4/5 and 8/5. So we're almost done. So we can write down our answer, actually. And here we go. So what do we have? Well, we have z equals 2 times a times x. Well, a is 8/5. So we get z is equal to 16/5. 2 times b times y. Well, 2 times b, and that is 2 times 4/5, which makes it 8/5. And that's got to be equal to the a squared plus b squared. Whoops. Not equal to. Subtract. Oh my gosh, I'm making so many mistakes here. Well, okay. What is a squared plus b squared? Well, it turns out, what is it? It's either 2 times a or it's 4 times b. So it doesn't really matter which one we use. So we can say 2 times 8/5 or 4 times 4/5, which makes it 16/5. And there we go. That's it. That's our answer. Now, if we wanted to, we can check. And how do we check? Well, we know, look, it satisfies this form because that's how we found A and B. It satisfies this form. And you can plug in 1, 0, 0, yep. 0, 2, 0, yep. It all works out. So other than that's a very thick minus sign, but that's all right. There we go. There we go. Life is good. Well, I think we have time for one more. One last one to help finish it up. So here we go. Find A and B so that the planes z equals x plus y minus 2 and z equals 4x minus 2y minus 14 are both tangent to the surface z equals 1 over ax squared plus 1 over by squared. So this is a sort of a different type of problem. See, we're actually looking for a surface which has a certain property. Instead of saying, oh, here's a surface, look for a tangent plane that has a certain property. So there's all sorts of shapes that can come out. Well, not really all sorts of shapes. But 1 over ax squared plus 1 over by squared correspond to bowls. And so we can have maybe a bowl that's very thin and narrow, we could, of course, have a bowl that's more shallow. And, of course, they don't have to be circles. They can be more ellipsoids in shapes. There's all sorts of possible candidates as you vary A and B for the bowl. It's deforming it in different ways. So we're after the particular bowl, the surface here, which happens to also have these planes as tangent planes. Now, one of the things that makes this interesting, or if you prefer the word challenging, is we aren't told where those planes are tangent. And so that actually is going to add a little bit of spice to our problem. But you know what? It's good to have a little bit of interesting challenges. If everything were easy, it wouldn't be fun. All right, so let's think about how we can approach this. So let's start by thinking about a generic plane. So what do we have? If I have my surface here, okay, I can think of my generic, I said plane, but I'm really saying generic tangent plane, right? So F at a point. Well, we're already using the symbols A and B, so I'm going to use a capital A and a capital B. All right, just so I don't confuse myself too much. Not any more than I need to, right? Okay, plus F sub x at A, B times x minus A plus F sub y at A, B times y minus B. So we'll go through and we'll simplify this. So we end up with a 1 over A times A squared plus a 1 over B times a B squared. Okay, plus, all right, now we can probably do this in our heads. The derivative with respect to x would be 1 over A times 2x. So that would become 2 over A times x, which we're plugging in capital A, times x minus little a. Sorry, x minus capital A. That should have been a capital A. Okay, good. Well, I was being faithful to copy it down. I just had written it down wrong before. And f sub y, okay, take derivative with respect to y. The first one goes away. It's 2 over b times y. So this would be 2 over little b times y, which is capital B, times y minus capital B. Okay, so, we get, if we clean this up, 2 over A times capital A, x, plus 2 over B times capital B, y, and then 1 over A, capital A squared, minus, because of that minus, 2 over A, capital A squared. So that becomes minus just 1 over A, capital A squared. Similar on this side here, see it's a 1 over B, capital B squared, minus 2 over B, capital B squared. So put it all together, get 1 over B, capital B squared. Okay, so that's our generic tangent plane. You give us a capital A and a capital B, boom, that's our plane. Now we have to think about what we have and how to use this information. So let's pick this plane right here. We're told it's tangent to our surface. And remember, this is, of course, z equals this. And we just sort of write it underneath, and we meditate for a moment on this. So we have z equals x plus y minus 2. And now let's meditate on this. And then we say, oh, wait a second. Things got to line up. Okay, cool. Well, what does that mean when we say things have to line up? Well, this 2 over A times A has to match up with that coefficient, which is really a 1. And 2 over B times B has to match up with that coefficient, which is 1. And 1 over A squared and 1 over B squared has to be 2. Now, look at what this tells us. this tells us that our capital A, if we move it across, is 1/2 little a. Because I'm just flip the A over 2, right? And here, this tells us that capital B has to equal 1/2 little b. All right, great. So put that in for this piece here. We have that 2 equals 1 over a times 1 over 2a, quantity squared. That's capital A squared. Yes, good. I don't know why I had so many parentheses. Plus 1 over b, and then capital B squared would be 1 over 2 little b squared. And if you clean this up, see how you have an a squared over a? Well, that's great. That makes this a 1/2 a. B squared over b, oh, not a 1/2, a 1/4. I'm sorry, because I forgot to square the 1/2. B squared over b, and then square root of the 1/2 makes a 4th b. And if you multiply both sides by 4, we come to the conclusion that a and b, if you add them up, have to be 8. So, this is progress. See, before we were like, A and B could be anything. And now we're like, well, A and B can't be anything. Whatever is true, they have to sum together to give us 8. Well, that's a good piece of information. That feels like we're halfway to solving the problem, because we're halfway to solving the problem. All right, so how do we do the other half? Well, we're going to do something very similar, just with the other plane, right? So let's write down our other plane. Well, it would be z equals 4x minus 2y minus 14. So 2 over a times a, so 2 over little a times big A, has to match up with the 4. So that says capital A, if we flip that 2 over a to the other side, well, so multiply 4 by a over 2, that's 2a. Here we have 2 over b times capital B has to match up with negative 2. So again, flip it across, and what do we come up with? Well, what we come up with is b has to be negative of little b. All right, great. And now we say, well, then there's one other piece of information. So the last coefficient says what? Well, 14 has to equal 1 over a times this capital A squared, say 2a squared, plus 1 over b times this capital B squared, that's negative b squared. And, well, we square it, we get 4a squared over a, so that's 4a. And here, b squared over b is b. So that tells us 4 times a plus b has to equal 14. Wonderful. So now we have a second equation. We now have 2 equations and 2 unknowns, and they're lovely equations in terms of a and b. They're the kinds of equations that we'd like to take home to meet our family. Mom, Dad, I've met a wonderful pair of equations, and we get along so well. So we're pretty much rounding the corner now. So we have our 4a plus b equals 14. A plus b equals 8. If we now subtract, we come to the conclusion 3a, and the reason we're subtracting is that we can straight cancel the b's. 3a equals 14 minus 8, which is 6. Okay, so that tells us that a has to equal 2. Once you know a equals 2, 2 plus b equals 8. Okay, so we now know that 2 plus b equals 8, which tells us b equals 6, and we're done. So our final answer, a equals 2, b equals 6. That will give us the exact right type of bowl. So that the bowl has the form 1 over ax squared plus 1 over by squared, and it happens to have both of these surfaces as, both of these planes, I should say, as tangent planes. Wow, cool. That's a fun one. You know, I'll be honest with you. Sometimes it feels like you don't have quite enough information, but you sort of have to play around and try things out. And I think the key for this one is to say, well, maybe I don't know where I'm tangent, but can I still extract information from knowing that I am tangent? And can I help me get anything that narrows it down? And the answer is yes. Yes, you can. As always, a good rule of thumb is try something. And if it doesn't work, try something else. I don't want to give you the impression that when I sit down and I say, oh, look, it's just automatic. You know, he does it. He hardly even thinks. It just flows like ink on paper. The truth is, I think about problems. Thinking about things is how you get better at solving problems. And if you're ever stuck, if you can, go for a walk. Walks are fantastic for clearing your mind and helping you sort things out. Do whatever you can to help get yourself more centered and think about things. Well, that was a lot of fun. I hope you learned something along the way, and that you come back, and that we'll see each other again in a future practice session. All right. Bye.